Something entered our solar system in 2025 that immediately raised a strange question. Where could an object like this possibly have come from? At first, it looked like another faint comet moving through the sky. But once astronomers calculated its orbit and began studying its chemistry, the picture became much more unusual. This wasn't simply a comet that had wandered in from the distant outskirts of our own solar system. Its trajectory showed that it was passing through the solar system on an unbound path, meaning it had originated somewhere beyond our planetary neighborhood. And then came the chemistry. Measurements of the material surrounding the comet suggested an isotope composition dramatically different from the comets we know. Its water contained an unusually high proportion of deuterium, while its carbon signatures also appeared unlike those normally associated with objects formed around our Sun. Those measurements led researchers toward an extraordinary possibility. This object may have formed billions of years before the Sun existed. The object was identified as 3I-ATLAS, the third known interstellar object detected passing through our solar system. Its story begins on July 1, 2025, when the ATLAS survey in Chile detected a faint moving object during its routine observations. At first, there was nothing especially dramatic about the discovery. Automated sky surveys detect moving objects constantly. But when astronomers calculated its orbit, the numbers immediately demanded a closer look. Its orbital eccentricity was calculated at roughly 6.14. That is far beyond the value expected for an ordinary comet bound to the Sun. An eccentricity of 1 represents the boundary between a gravitationally bound orbit and an escape trajectory. A value above 1 indicates that the object is moving through the solar system on an open path. At 6.14, this was not something that had simply spent millions of years circling the Sun before finally coming inward. It was passing through. The implication was straightforward but extraordinary. 3IATLAS had originated outside our solar system. That made it only the third confirmed interstellar visitor we had ever identified. The first was 1I, Oumuamua, discovered in 2017. It behaved so strangely that astronomers spent years debating exactly what kind of object it was. The second, 2I, Borisov, appeared in 2019 and looked much more familiar. It behaved like a comet, complete with a coma and recognizable cometary activity. 3IATLAS added another piece to the puzzle, but its trajectory was particularly extreme. Its excess velocity relative to the Sun was around 58 km per second. That velocity became important because it provided clues about the object's journey through interstellar space. Astronomers studying its motion estimated that it could have been traveling through the galaxy for an enormous amount of time. Earlier calculations allowed a broad range of several billion years, while later isotopic measurements pushed the possible age much farther back, toward roughly 10 to 12 billion years. For comparison, our Sun is about 4.6 billion years old. So if those age estimates are correct, 3IATLAS could have existed before the Sun, before Earth, and before our entire planetary system took shape. But the most interesting part of the story wasn't simply its age. It was what the comet was carrying. During its journey toward the Sun, astronomers around the world attempted to observe it as continuously as possible. This became particularly important during a period when several major observatories were unavailable or occupied with other operations. That created a gap in the observations at an unfortunate time. For a normal comet, missing a short period of activity might be frustrating. For a fast-moving interstellar object that would never return, it could mean losing information that could never be recovered. The comet was changing rapidly as solar heating increased. Its brightness was changing, gases were escaping from its surface, and material was forming the surrounding coma. So continuous observation mattered. During this period, observatories in China continued monitoring the object. Facilities located in regions including Tibet and other high-altitude areas were able to provide additional observations while several major Western facilities were unavailable. Those observations helped maintain a continuous record of the comet's movement and brightness. The importance of that data wasn't necessarily obvious to the public. There was no dramatic announcement attached to every observation. Much of astronomy simply works this way. Telescopes collect measurements, the data is calibrated, archived, and eventually combined with observations from other facilities. But when researchers later combined the different datasets, those additional observations helped reduce uncertainty in the comet's position and activity. And this highlighted something important about modern astronomy. The largest telescope isn't always the most important telescope. A giant observatory can collect incredibly detailed information, but if it happens to be unavailable at exactly the wrong moment, another smaller facility that is already watching can become extremely valuable. For an object like 3I/ATLAS, continuity can be just as important as raw telescope power. Then came one of the most revealing stages of the investigation. The James Webb Space Telescope observed 3I/ATLAS as it moved away from the Sun after its closest approach. By then, solar heating had caused material on and around the comet to release gases into space. That created an enormous opportunity for spectroscopy. Instead of simply taking a picture, Webb could examine the light from those gases and determine which molecules were present. And the chemistry was unusual. One of the first things that stood out was the comet's water. Water normally contains ordinary hydrogen, but a small fraction of hydrogen in nature exists as deuterium. Deuterium is a heavier form of hydrogen because its nucleus contains an additional neutron. The ratio between deuterium and ordinary hydrogen can act like a chemical fingerprint. It provides clues about the environment in which water formed. Across objects in our solar system, scientists have measured a range of deuterium to hydrogen ratios. Those measurements help researchers understand the conditions that existed when the solar system formed billions of years ago. But 3I/ATLAS appeared to be very different. Its water showed a deuterium to hydrogen ratio roughly 30 times higher than typical solar system comets, according to the measurements described in the source material. That is not a small difference. It suggests that the water inside this object formed under conditions dramatically different from those associated with the material that eventually became our solar system. And that raised another question. What kind of environment produces such an unusual isotope ratio? One possibility involves extremely cold formation conditions. At very low temperatures, chemical reactions can favor the incorporation of deuterium into molecules such as water. Over long periods, that enrichment can become significant. So the chemistry of 3I/ATLAS points toward a cold and unusual birthplace. The carbon isotope measurements added another layer to the mystery. The carbon signatures detected in the comet also appeared inconsistent with familiar solar system material and with some nearby star-forming environments. When astronomers combine these clues, they can begin working backward. They aren't simply asking, how old is this comet? They're asking, what kind of molecular cloud could have produced these ratios? How cold was that environment? What was the chemical composition of the region? How long did the object remain there before being expelled? And what happened to it during billions of years of travel between stars? The answers remain uncertain. But the chemistry strongly suggests that 3I/ATLAS did not form under conditions identical to those that produced our own solar system. Another surprising measurement came from the gases surrounding the nucleus. The ratio of carbon dioxide to water appeared unusually high. In many familiar solar system comets, water is a major component of the volatile material, while carbon dioxide is present in smaller proportions. For 3I/ATLAS, the reported carbon dioxide to water ratio was dramatically higher. Carbon monoxide was also abundant compared with water. These measurements give researchers additional clues about the environment in which the comet's ice is formed.